Hi, Dr. Liu. This is my sorting visualizer application. I have built this one by using Java language and JavaFx application, JavaFx package. This application is a visualization for different sorting algorithms, purpose sort, selection sort, insertion sort, share sort, quicksort, and merge sort. And over there, I have a capacity box to enter the number of values that I want to be sorted. For example, in this case, I can generate an array of 1000 number. So the my string show me 1000 bar with very small width, and the length of this bar they vary depend on the values of number. And because so I may want to change the number of values to be 100. So I got 100 rectangle bars with different lengths, and I can sort this number by selecting one of these buttons. I want to store with purpose sort. And so with purpose sort, as the visualization show me how it somehow show me how it work, the two application number are being compared, and as they are not in the right order, they are being swapped. And the larger number is popping down to the right side of the list. And the sorting visualizer application also show me the running time. The running time over there is not the time it takes to complete the visualization. It is only the time to complete the sorting. And it also show the number of comparison, around 5,000 comparison to complete this task. As you can see, the largest number has been purpled out to the list, and thus the color of it has been changed. Because it takes quite slowly to complete the sorting by using purpose sort, so I'm not gonna wait until the list is sorted. I can use the undo button, so to bring my array back to its beginning state when I have not clicked on the purpose sort button, so that I can use different sorting method to compare with the purpose sort. With purpose sort, it takes around 250,000 nanoseconds. But how about selection sort? Selection sort, the running time is quite closer to the purpose sort running time, because they both, the time complexity on the worst case is both big O of n square. That means as the size increase, their time running, the execution time increased quadratically. So, and this visualization show me that with selection sort, the smallest number in the sublist is picked and it is moved to the beginning of the sublist. This number already sorted. That's why the colors of these bars has been changed. And I may want to try with insertion sort. So with insertion sort, in this we can see the running time is much, to complete the sorting process is much faster than in selection sort and purple sort, which is around 200,000 nanosecond, but this one is just around 55,000 nanosecond. Maybe because with this particular kind of array, but generally speaking, insertion sort time complexity is also big O of n squared in the worst case, and also when the size increase, the time it takes to complete the sorting in the worst case also increase with a quadratic formula. And as we can see with insertion sort, the number in a particular index is compared with the element before it, which are already sorted, and compare until it reach to the right place. So that's why if the number very small like this one, to be moved to the beginning of the list, to the left of the list, to its right place, it takes quite a lot of move, quite a lot of compare, quite a lot of comparison to be moved to its right place. Because of that, there is an improvement by using shell sort. The author of this sorting algorithm, he want to improve the performance of insertion sort. So the gap is added into insertion sort. Instead of sorting with the gap which is 1, with shell sort, the gap, starting the gap is big, so that the smaller number can be moved to the left faster and the larger number can be moved to the right faster. And as the process go on, the gap is reduced until the gap reaches to 1. And when the gap reach to 1, is the shell sort just become the insertion sort. But when the gap reaches to 1, when the gap reaches to 1, it takes less move, less comparison, less number of comparison, less number of move to move a particular number to its right place on the left side, because smaller number is already on the left side and the larger number is already on the right side. as you can see, the gap between two numbers that are being compared reduced after each pass. And as you can see, over there, the number of comparison is much lesser than the number of comparison of purple sort, which is around 5,000 number of comparison. So you can see the smaller number on the left side and the larger number on the right side of the array. And by using the visualization, it's easier to understand how the sorting algorithm works. So how about try with Quicksort? So in average case, Quicksort, the time complexity of Quicksort is big O of n log 2 n, and as you can see, the running time is much more efficient, much faster than the previous sorting method that we have used, just 45,000 nanosecond. Though and you can see this is the pivot number. The left element, they are less than the pivot number, and the right elements, they are larger than the pivot number. This one also like this, the left side elements are less than the pivot number, and the right side are greater than the pivot number. This is how the Quicksort works. And this is also called divide and conquer approach. And how about trying with merge sort? So merge sort, also this case merge sort, it takes greater than Quicksort, but not much. But the merge sort generally with in the worst case, the time complexity is still big O of n log 2 n, though the Quicksort in the worst case the time complexity is big O of n square, but with merge sort the time complexity in the worst case is just still big O of n big O of n log 2 n. So merge sort have better performance than Quicksort, and the visualization also somehow show how the merge sort work. The two sublists will be sorted and they are merged together. This one already sorted, and this sublist when once this sublist is sorted, the two will be merged. At the beginning, the sublist is just the one number, and then they merge, but the process continue to the sublist of two, the two sublist of two merge, and then the two sublist of three merge, and continue until the half one already sort and this half one already sort, and they merge to become a completed sorted list. With my coding, I define for my project package. I define four main no three main classes. The first one is sorting visualizer, and in this one I define the features for my scene, the pen, the layout, VBox, toolbox, test, buttons, test, and also slider, and also set the action for my buttons. I don't think that using the button is an efficient way, but because I am familiar to use button to set an action when I click on the button, so I choose to use it. And I also define an fx array in which I initialize a random array of number, process the sorting, and create the visualization for the sorting. This is the constructors, and over there I define different sorting methods: shell sort, quicksort, and merge sort. In this class, I used to define the transition when I swap to bars. I use field transition, translate transition, parallel transition, as well as sequential transition. This is the first time I use it. When I started to make this visualizer, I don't know how to make the animation, and it takes me quite a long time to figure out that to make the animation I need to use the transition, and then I need to learn how to use transition, and a lot of struggle, but now I'm happy that I have learned it. And I also define the array class. In this array class is quite similar to my fx array. It also performs the sorting method, but in this class, the sorting method is created to obtain the parameters such as the running time and the number of comparison. For sort, I use the system.nanoTime to obtain the time when I start the sort and obtain the time when I complete the sort, and subtract them to obtain the running time. So I do it similarly with other sorting algorithm. And I also define an interface for my color, because I don't want to use it with the hexa number. I want to use it with the name so that I can know which color I am using. And I obtain the hexa number that represent a particular green color by searching on the internet. I also can use number of red, green, blue instead of hexa number, but I choose this one. Overall, I think my coding designs is not efficient way, but still I make it. I am curious to make the sorting visualizer, and finally I accomplished the thing that I want to do, and I'm happy to hear the feedback and comment from you. And thank you for watching. I hope you enjoy my presentation. Thank you.